Welcome to this comprehensive guide on C# concurrency, a fundamental concept for building responsive and efficient applications. Mastering concurrency is key to unlocking the full potential of your C# programs, ensuring they handle complex operations without freezing, thus providing a seamless user experience. Concurrency allows your program to handle multiple tasks seemingly at the same time, dramatically improving overall application performance. By utilizing available resources more effectively, it significantly enhances the user experience, preventing the application from becoming unresponsive during intensive operations. Concurrency is crucial for applications that need to remain responsive while performing long-running operations, such as processing large datasets or fetching data from web services. Without it, these operations would block the main application thread, leading to a frozen user interface and a frustrating user experience. We'll explore various C# concurrency models, each offering different levels of abstraction and control. Our journey begins with the foundational and low-level concept of threads. Understanding threads is essential as they form the underlying mechanism for many higher-level concurrency constructs in C#, providing the bedrock for advanced techniques. A thread is the smallest unit of execution that an operating system can independently schedule. Within a single process, multiple threads can exist, each executing instructions concurrently. This independence allows your program to perform several operations simultaneously, such as updating the UI while fetching data, without one blocking the other. In C#, you can create a new thread by instantiating the system. Threading, thread class. You pass its constructor a delegate, like threadStart or parameterized threadStart, which encapsulates the method or code block the new thread will execute. This delegate defines the specific work the newly created thread is responsible for carrying out. Once a thread object is created and its work defined, you initiate its execution by calling the start method on your thread instance. Upon invocation, the operating system allocates resources and schedules the new thread, which then begins executing the method specified by the delegate. This action brings your new thread to life, allowing it to run concurrently. However, managing raw threads can be complex, leading to significant overhead. Each thread requires its own stack and kernel resources. If not handled meticulously, this can quickly lead to resource exhaustion, where the system runs out of memory or other vital resources, severely impacting application stability and performance. Each new thread consumes valuable system resources, including memory for its stack and CPU time for context switching. Creating too many threads can paradoxically degrade application performance instead of improving it. The overhead of managing excessive threads can outweigh concurrency benefits, leading to slower execution and increased resource contention. This is where the C# thread pool comes into play, offering a more efficient way to manage worker threads. The thread pool is a managed collection of worker threads readily available to execute tasks. It simplifies thread management by abstracting away the complexities of thread creation and destruction, providing an optimized approach to concurrent operations. The thread pool maintains a pool of pre-initialized worker threads, ready to execute tasks. These threads are created once and reused for subsequent tasks, eliminating the significant overhead of repeatedly creating and destroying threads. By reusing threads, the thread pool drastically reduces resource consumption and improves the overall efficiency and responsiveness of concurrent applications. You can queue a work item to the thread pool using the static method threadpool.queueUserWorkItem. This method requires a wait callback delegate, pointing to the method containing the work to be executed. You can also provide an optional state object to pass data to your callback method, making it flexible for various task requirements. Once a work item is queued, the thread pool intelligently assigns it to an available worker thread from its managed pool. This optimized assignment ensures efficient thread utilization. By continuously reusing existing threads for new tasks, the thread pool minimizes new thread creation, significantly reducing system resource consumption and improving application scalability and performance. While the thread pool is more efficient than raw threads, the Task Parallel Library, or TPL, provides an even higher level abstraction. TPL is designed to simplify parallel programming and asynchronous operations, building upon the thread pool. It offers a richer, more expressive, and powerful framework for handling complex concurrent scenarios in C#. TPL introduces the task class, a powerful construct representing an asynchronous operation. A task is a higher-level abstraction focusing on the work to be done rather than the thread that does the work. This modern and flexible approach allows developers to compose complex asynchronous workflows more easily, providing better control over execution flow and error handling. Tasks are built on top of the thread pool, but provide richer features like continuations, error handling, and cancellation. Continuations allow specifying actions after a task completes, whether successfully or with an error. Tasks also offer robust mechanisms for structured error handling and cancellation, simplifying the management of asynchronous operations and building resilient applications. You can create and run a task using the static task run method. This method takes a delegate, often a lambda expression, representing the asynchronous work. Task run intelligently queues this work to the thread pool for execution and immediately returns a task object, allowing you to monitor its progress, await its completion, or chain further operations. The async and await keywords dramatically simplify asynchronous programming in C#, allowing you to write non-blocking code that looks synchronous. Marking a method with async indicates it can contain await expressions. The await keyword pauses an async method until an awaited task completes, ensuring the calling thread remains non-blocked and responsive. When you await a task, the current method pauses without blocking the thread. The thread that initiated the await is immediately returned to its caller, freeing it up for other work, like updating the UI. Once the awaited task completes, the remainder of the async method resumes execution, often on a thread pool thread, ensuring efficient resource utilization. This powerful combination of the task class, async, and await keywords makes TPL the preferred and most idiomatic choice for most modern C# asynchronous operations. Its high-level abstraction, robust feature set, and simplified syntax are superior to direct thread or thread pool management for building responsive, scalable, and maintainable applications. However, when multiple threads or tasks access and modify shared data simultaneously, you can encounter race conditions. These occur because the exact timing and interleaving of operations from different threads are unpredictable, leading to potential data corruption or inconsistent states, if not properly managed and synchronized. A race condition occurs when the outcome of a program depends on the unpredictable timing of multiple operations. The final result becomes dependent on the specific, unpredictable order in which multiple threads execute. Since the operating system's scheduler determines this timing, results can vary, making race conditions notoriously difficult to debug and reproduce consistently. To prevent race conditions and ensure thread safety, C# provides synchronization primitives like the lock statement. The lock statement is designed to enforce thread safety by creating a critical section of code. It ensures that only one thread can execute that specific block of code at any given moment, thereby protecting shared resources from concurrent modification. The lock statement ensures that only one thread can execute a critical section of code at a time, guaranteeing exclusive access. When a thread acquires a lock, no other thread can enter that section until the first releases it. This serializes access to shared resources, preventing multiple threads from simultaneously modifying them and safeguarding against data corruption. To implement a lock statement, you define a dedicated lock object, typically a private, read-only reference type object like private read-only object _ lock object equals new object. You then wrap the critical code, which accesses the shared resource, within the lock block. This ensures the lock is properly managed and helps prevent deadlocks. Employing the lock statement guarantees exclusive access to the protected code block and its shared resources. This critical mechanism prevents multiple threads from simultaneously reading or writing to the same data, which is the root cause of race conditions. The result is robust data integrity, eliminating data corruption and preventing unpredictable program behavior, leading to more reliable applications. In summary, C# offers various concurrency models, each meticulously designed and optimized for different programming scenarios. From low-level thread management to high-level asynchronous programming, understanding these options allows developers to choose the most appropriate tool. This ensures both efficiency and maintainability in their concurrent applications, a cornerstone of modern C# development. Raw threads provide low-level control over execution but come with significant management overhead. They require manual handling of creation, starting, stopping, and synchronization, which can be error-prone and resource-intensive. While powerful for specific, highly optimized scenarios, their direct use is generally discouraged for typical application development due to complexities and potential resource exhaustion. The C# thread pool significantly improves efficiency by managing a collection of worker threads and reusing them for queued work items. This approach eliminates the overhead of repeatedly creating and destroying threads, leading to better resource utilization and faster execution of short-lived tasks. It provides a more managed and optimized environment for concurrent operations. The Task Parallel Library, or TPL, with task, async, and await, is the modern, high-level, and preferred approach for most asynchronous operations in C#. It offers unparalleled simplicity in writing complex concurrent code, provides robust error handling, and ensures responsiveness without blocking threads, making it the go-to solution for building scalable and maintainable applications. Finally, lock statements are essential synchronization primitives for ensuring thread safety and preventing race conditions when multiple threads or tasks access and modify shared data. By enforcing exclusive access to critical sections of code, lock statements guarantee data integrity and predictable program behavior, vital for the reliability of any concurrent application manipulating shared state. Choose the right concurrency model based on your specific needs and the nature of the task. For most new development and general-purpose asynchronous operations, prioritizing the Task Parallel Library with async and await is highly recommended due to its simplicity, robustness, and efficiency. Understanding threads and the thread pool provides deeper insight into underlying mechanisms. Mastering these fundamental C# concurrency concepts, from raw threads and the thread pool to TPL with async and await, and thread safety with lock statements, will empower you. You'll build highly performant, responsive, and robust C# applications that effectively utilize modern multi-core processors and deliver exceptional user experiences.